Hi everybody. As you can see here, we've included now video into these little presentations. And what we're going to do today is we're going to talk about cell potential and free energy. I alluded at the beginning of the unit that there is a connection between thermodynamics and electrochemistry, and we're going to see that connection overtly here in this video. Alright, so let's get the title out of the way and let's get right into taking a look at some of the math that shows us this connection. Alright, so we've been talking about cell potential in class, and as we know, cell potential is measured in volts. And perhaps you remember that a volt turns out to be a joule per coulomb, alright, a J per C, joule per coulomb. And joule is a unit for measuring work, and coulomb is a unit for measuring charge. So a volt is really the amount of work that can be done per unit charge. Now you see here we also have a negative sign in the relationship because we want to show work leaving the system. The volts that a galvanic cell puts out are actually headed out of the system. They're something that they are volts that we can do some work with, so that's why we have that minus sign. Alright, so all of this implies then that voltage, which we represent cell potential, usually using that sort of epsilon squiggly E symbol here, will be equal to then negative W divided by Q, the work divided by the charge. Now we learned in thermodynamics that the free energy of a system is ultimately equal to the work that the system can output. So delta G is equal to W. And as we continue on the connection here and we rearrange this equation here for work, we see that work is equal to negative QE. Alright, so now we just have to keep going a little bit further. Now we have here the issue of charge, Q. How much charge are we passing when we do these electrochemical expressions, these electrochemical experiments? Well, then we need to know the charge for a mole of electrons. Because when we do electrochemistry, we're transporting moles of electrons. And it turns out that 1 mole of electrons has a charge of 96,485 coulombs. Or if you want to play with 3 sig figs, 96,500 coulombs. And that quantity, that charge per mole of electrons, was first determined by one of the great experimental chemists of all time, Michael Faraday, and so this unit is associated with his name, and we call it a Faraday, and it's often abbreviated with the letter capital F. So now we've kind of come full circle here. We have our free energy, delta G, which is equal to the release of charge times the cell potential, negative QE, and we can then equate that to negative NF squiggly E, where N are the moles of electrons being exchanged in the electrochemical experiment. F is Faraday, the charge of a single mole of electrons, times the cell potential. Alright, and so all of that allows us then to ultimately have the grand relationship that I'm going to show here in a box, that the cell potential, that the free energy, delta G, is equal to negative NF squiggly E, the cell potential. And we have this equation in two different forms. At non-standard states, so without the little superscript 0, or at standard states with the superscript 0. So delta G equals negative NF times the cell potential. Alright, let's take a look at an application of this. And an application is actually calculating the cell potential of redox reactions. We've seen that, we've looked at that at galvanic cells in class, and we looked at how you take the cell potential of the cathode reaction and add it to the cell potential for the anode reaction, and just take those numbers off of the chart and you combine them. Well, it turns out that that calculation you're doing when you're doing the cathode and the anode potentials combined, it turns out that that's actually a free energy calculation. Let's take a look at an example. Alright, so what I want to do is I want to find the cell potential for the full redox reaction we have here down at the bottom. And we're going to get it from the relevant half reactions. We have the reduction of aluminum 3, and that has a potential of negative 1.66 volts. I'm getting this right off of the potential chart we gave out in class. And then we have the reduction of magnesium 2 to elemental magnesium for negative 2.37 volts. So what we're going to do is we're going to combine this into a spontaneous redox reaction where we reduce aluminum 3 to aluminum and oxidize magnesium to magnesium 2. And you see there I have the coefficients to go ahead and balance it. So what I'm going to show you is that when we do the calculation here, we're actually doing a free energy calculation. So what we'll do is we'll call the first equation, the free energy of that first equation, we'll call that delta G1. The free energy of the second equation, we'll call that delta G2. And then the free energy of our target equation is going to be delta G3. Now, just like you're applying Hess's law, what would delta G3 be with respect to G1 and G2? Well, delta G3, which is the free energy of the target equation, that's going to be equal to twice the delta G of the first equation, minus, because I have to flip this second equation, I'm flipping it, minus 3 times the delta G of that second equation. So I'm going to get the cell potential by using this new delta G equals minus NF squiggly E relationship we developed and show you that cell potential calculations are ultimately free energy calculations. Okay, so we're going to start where I've got at the bottom of the screen here that equation for delta G3, and we're going to combine all of this and see how this works. Alright, so let me shrink this down. I'm going to move it over here, but so that we can still see most of it, hopefully. And I'm going to bring over the actual work. Okay, so here's where we ended. Delta G3 is equal to 2 times G1 minus 3 times G2. So that's the Hess's law analysis for finding the free energy change of the target redox reaction that we have there. You can see up there on the right. So now I'm going to substitute in this new relationship that we developed up here. You can still see it, the delta G equals minus NF squiggly E. So I'm going to plug in negative NF squiggly E for each of my G terms. And I'm going to have an N3 there, that's the moles of electrons that are exchanged in the target equation, our G3 equation, times F times squiggly E, which is the cell potential for the third equation. That's actually our unknown. We're looking for the value, ultimately, of squiggly E3. So that'll be equal to negative 2 times N1F E3 minus a negative, so plus 3N2F E2. I'm solving for E3. I'm trying to find the cell potential for that target equation, so squiggly E3. When I rearrange and isolate E3, I get the equation you see there, 2 times N1 E1 minus 3 times N2 E2 divided by N3. Now, I'm just going to start plugging in my values. So E3 is going to be twice the delta G term. Now, N1 are the moles of electrons that are exchanged in the first equation. And if you look back up here at our problem, you see that our moles of electrons that are transported in that target equation are 3, right? I have 3 moles of electrons up there. So 3 moles of electrons are being transported, so that's why I have that 3 there. And then the cell potential for the first equation off of the chart was negative 1.66. Minus 3 times the moles of electrons in the second equation, which is 2, times the cell potential from the second equation. Again, we get that right off the chart, negative 2.37 volts, all divided by N3. Now, if you look at our overall reaction that I'm solving here for N3, we see in this target equation here, what I'm transporting here, if you look at the moles of electrons being transported, it's 6 electrons that are coming and going. I have 2 moles of aluminum 3 turning into 2 moles of elemental aluminum. That's a change of 3 electrons, but times 2 moles, so that's 6 electrons that I'm transferring. Or I have 3 moles of magnesium 0 going to 3 moles of magnesium 2, so then that's 2 times 3 gets you to 6 electrons as well. So that's why I have a 6 in the denominator for my E3 expression. Now notice what's going to happen here. I have 2 times 3, 3 times 2, and I have 6. If you remember, we told you when you calculate cell potential, you don't multiply by any manipulating coefficient that you multiply the half reaction by. And that's because it turns out in a full redox reaction, the moles of electrons coming and going have to balance out. So these multiple times n factors will ultimately cancel out. All right, so then you see we're left with the calculation we've been doing. We have the cell potential for the cathode reaction being added to the cell potential for the oxidation, and we are left with 0.71 volts. It's a positive potential, so it tells me we have a galvanic cell here. It's spontaneous, but it's not a very good battery. Nobody's going to be using this magnesium-aluminum setup to generate much current, but it at least is spontaneous, and we have 0.71 volts. So there we have it. There is our connection between free energy and cell potential. All right, that's it for now.